Sorry, mute your go bad.
No. Because we have been desiccated. J'ai eu des problèmes ici.
Would you like to full screen? So I think maybe just use the laser and
Yeah. Okay, sorry about that. So, hi everyone. For the next 30 minutes, I would like to, first of all, I want to thank the organizers for giving me the opportunity to share my work with you today. And I would like to talk specifically about these two papers that we put out in collaboration with Aris Zonos back in October. And the topic of my talk is going to be the critical dynamics of superfluid. So the problem is the following one. We want to study superfluids close to the second order phase transition, close to the instability. And the thing is that near the critical temperature of the instability, the usual conventional superfluid hydrodynamics break down. And so we need an enlarged EFT in order to describe our system. The reason for the breakdown is that we have a certain almost massless degree of freedom that we don't take into account when we study conventional superfluid hydrodynamics. And the way to solve the problem, as we're going to see, is that we include this extra degree of freedom and everything works out correctly. This is the big picture. Okay, so first, I'm going to talk about a little bit about hydrodynamics and how hydrodynamics break down when we're close to phase transitions, second order phase transitions. Then we're going to see how one can build such an EFT close to a critical point. And then towards the end of my talk, I'm going to talk a bit about how holography tackles exactly the same problem. And in particular, how holography can give us exactly the same EFT one can build phenomenologically. So what is hydrodynamics? Hydrodynamics generally is an effective theory that describes finite temperature systems and main body systems that are usually close or maybe out of thermodynamic equilibrium. And it is an effective theory that this is something that we have to keep in mind. It's an effective theory that is actually valid when you go at large wavelengths and at late times. And it is valid in principle only in this regime. And the reason for this is that whatever microscopic degrees of freedom you have in your theory, this usually takes some specific time, let's say, they need some mean-free path in order to actually diffuse in your system and relax. But when you have conserved charges in your system, like energy or charge density, exactly because they are conserved, in a sense, they are protected. So they cannot be destroyed locally. So in order for a charge to go back to equilibrium, it has somehow to spread across the system in order to relax. And hydrodynamics in this way provides a universal framework. We don't care about the actual microscopics of the system you're trying to model. And it is often helpful when you don't have quasi-particles or generally a weakly coupled prescription to describe your dynamics. And for what I'm going to talk about here, hydrodynamics for us is going to be just a classical theory. So we're looking at classical equations of motion. Although one can take into account fluctuations, whether one puts them by hand in his equations, or one can study fluctuation systematically through a framework called Kailidis formalism. I might have time to say one or two things about this formalism towards the end. So, for simplicity, we're going to assume that we have a certain system that is invariant under translations and also invariant under the Lorentz group. So we have Poincare symmetry, and probably we have also some kind of global Yuan symmetry for to be concrete. And Nether told us quite a while back that exactly because we have this continuous symmetry, we don't have conserved currents in our theory. Namely, we're going to have the stress tensor in our theory, and we're going to have a conserved current due to the global Yuan symmetry that we assume. So Nether's theorem gives us for free the equations that we want to study. These are the conservation laws are just the equations of motion of hydrodynamics. But what are the effective variables of hydrodynamics? So in order to think about this question, we have to go back a step back and think about thermodynamics. So global thermodynamic equilibrium. In order to describe thermodynamics, one usually uses a temperature to describe his or her system, a chemical potential when we have a global symmetry associated to it, and probably a fluid velocity when we want to actually fix our inertial frame. Also, sometimes we're going to study a system in background sources. So for simplicity, we might have an electric, a static electric field, or a metric more generally. And now we take these variables of thermodynamics, and in hydrodynamics, we do the following. We say, okay, these are constant in thermodynamic equilibrium, but what if they start to vary, but only weakly across space-time? So they become fields that live in our space-time, but they change only slightly. And exactly because they change slightly, the derivatives are small, and this enables us to actually construct a perturbative expansion. So what we do is we take our conserved currents, and we say we're going to expand these conserved currents in a certain perturbative scheme where we count derivatives of the hydrodynamic fields of temperature, chemical potential, and so on. So we are going to say that we expand the stress tensor. The first term here will not include any derivatives. The first one is going to include only first derivative of these variables of temperature and so on. And these expressions are going to be what we call constitutive relations in hydrodynamics. Now, again, we imagine a system, a Lorentz invariant system with a global symmetry, and assume that this symmetry is not spontaneously broken. At the lowest one I show without any derivatives, these are the constitutive relations in the first line over here. So we don't include any derivatives, and we just use the fluid velocity, the chemical potential, and the temperature. And this epsilon over here is just the energy density of our system, and this P is the thermodynamic pressure. Now, when we go at first order in derivatives, we're going to have three terms. In particular, this term over here, which is given by this expression, it includes derivatives of the fluid velocity, and this is what we call a shear viscosity. Another term that includes derivatives of the fluid velocity again, and this term is called the bulk viscosity. And the same game we can play it for the current. And this sigma over here is the conductivity. So we have derivative terms, and in front of them we have order 1 coefficients. These order 1 coefficients are what we call transport coefficients. And basically what we are doing is that we hide all our ignorance about the microscopics of our system in these specific coefficients. So in principle, they can be arbitrary functions of the intensive variables of our thermal state. But they have to satisfy certain phenomenological constraints that we impose on top of this theory that we have discussed so far. And one is that we have to have a notion of a second law of thermodynamics, basically that the entropy grows. And Another thing is that we have to respect the discrete symmetries of our system, and in particular, whenever we have a time reversal invariant system, we have to have what we call Onsager reciprocity. These two phenomenological constraints are going to give us some interrelations between these transport coefficients. Now, the system that we actually want to discuss in this talk is going to be superfluids. Generically, we can describe superfluids as a state of matter where we have a global continuous symmetry, which is continuously broken. So we follow the Landau paradigm of phase transitions, and we assume that above a certain temperature, everything is not spontaneously broken, but starting from a certain critical temperature, a certain operator called the order parameter develops a vacuum expectation value, so it becomes non-zero, and exactly because it becomes non-zero, the U1 symmetry that we're talking about is spontaneously broken. So basically what I plot here is just the profile of the order parameter in the thermal state, and on the right hand over here, I just have the free energies of the two competing phases. So we have the normal phase without any symmetry breaking, and the broken phase that it becomes thermodynamically preferred, so lower free energy, below a certain critical temperature. Now, for hydrodynamics, what is going to be important for us is Gaussian theorem. So Gaussian theorem tells us that whenever we have the spontaneous breaking of a symmetry, we're going to have a massless degree of freedom in our theory. So exactly because we have the spontaneous breaking of the U1, we're going to have an extra hydrodynamic degree of freedom. And this is precisely the phase of the order parameter over here that transforms under the U1 with shifts. And this is basically the superfluid component that is going to be added on top of the normal fluid that we discussed before. So again, we have chemical potential, temperature, normal fluid velocity, but now in superfluids, we also have the phase of the order parameter. So this is what the constitutive relations of superfluid hydrodynamics look like. Again, here I have the relations at zeroth order in derivatives, and here at first order in derivatives. You can see that we have terms exactly like we had in the normal fluid case, but now we have new terms, even at zeroth order, that include this fluid velocity, this superfluid velocity that shows up because of the phase of the order parameter. I want to draw your attention to this term over here. So this is what we had in normal fluids. We have also another term, which we call a supercurrent. This is just a combination of the phase of the order parameter over here. And this is what we call a supercurrent. And this is what we understand when we talk about superfluids. We think of a current that flows without any dissipation, on and on. And this is precisely this term over here. And this is everything about the constitutive relations at zeroth order. Now, we said that we have an extra degree of freedom. So we have somehow to fix its time evolution, even at equilibrium. And the point is that in order to do that, we have to introduce a certain relation called a Josephson relation, which does exactly that. It fixes the time evolution of the phase of the order parameter at equilibrium. And it turns out that it has to be equal to the chemical potential of our theory, the chemical potential associated to the U1 of our theory. Now, at first order in derivatives, again, we have terms similar to the normal fluid case, but again, we have new terms that include the superfluid velocity and derivatives thereof. So we have, specifically, we have these three terms, zeta1, zeta2, zeta3, that I want you to keep in mind, which are called the superfluid path viscosities, which again are new transport coefficients that describe the superfluid state that we want to study. So far, we have done the following. We have described how hydrodynamics deals with the low energy description of our system in this region over here, so above TC. We have described how hydrodynamics deals with our system below TC, but with a certain assumption that we are far away from the critical point. Remember the big if that I had over here. We are assuming that, okay, derivatives are small, like always in hydrodynamics, but in a certain sense, they are smaller than the distance from the critical point. The question we want to ask now is what happens when this derivative is almost the same as the distance from the critical point. So we are interested in this region over here. What happens close to the critical point? How we can describe our system? And the thing is that remember these bulk viscosities over here in the superfluid case. These bulk viscosities, whenever we approach the critical point, blow up. So we said these are order 1 coefficients. But what happens when they blow up? It means that our perturbative expansion breaks down. So something went wrong. And as usual in perturbation theory and effective theories, whenever we have divergences, usually we have lost some almost massless degree of freedom that we didn't take into account. And this is precisely what happens here. Close to the critical point, apart from the phase of the order parameter, we also have the amplitude of the order parameter that becomes nearly massless. And we have to take into account in order to build our EFT. So before I go into how one can build such an EFT, are there any questions? Okay. So this is the setup of our problem. For those who are familiar with the literature, I'm going to say that what we did is that we expanded previous theories from the 70s, which include the order parameter in the near critical dynamics, but also expand in the sense that we include the normal fluid component. So we have the temperature and the fluid velocity in the game as well, apart from the order parameter and the charge. In general, in the field theory, we can include external sources and take derivatives, functional derivatives with respect to these sources, and define our conserved currents. So the stress tensor and the current. In the same way, we can include an external source for conjugate to the order parameter and take derivatives and find the order parameter. Now, if we assume that this generating functional is invariant under diffeomorphisms and U1 gauge transformations, we can get for free again the conservation laws of hydrodynamics. These are the same as before, but the only difference is now that we have external sources turned on. So we have a metric. This is why we have covariant derivatives over here instead of simple derivatives. And we have an electric field, and this is just the field strength associated to it. And we have external sources for the order parameter as well. And this is why the current is not exactly conserved. But we have another degree of freedom, so we have to specify the equation of motion for it, which is not included in these two conservation laws. First of all, let's think of equilibrium in our system. In general, we can define equilibrium by saying that I have a certain time-like Killing vector in my system, and I want the lead derivatives acting on the external sources of our system to give me something trivial. In particular, we want, in simpler terms, we want time derivatives to be zero in equilibrium. This is what one would intuitively say about equilibrium. We don't want things to change in time. And in fact, we can define our thermodynamic variables in equilibrium, so the temperature, the fluid velocity over here, in terms of this Killing vector that defines our equilibrium state. And moreover, the same thing we can say about the order parameter. We don't want the amplitude of the order parameter to change. And the phase of the order parameter, we want it to change up to a gauge transformation. So if we combine these two, we get this expression over here, which holds only in equilibrium. So this expression over here includes both this expression for the phase and the amplitude of the other parameter. Again, I emphasize what I say here is only valid in equilibrium. Now, remember this expression for the generating functional I wrote over here. In general, we can think of it as a path integral over some degrees of freedom of our theory. And here the weight is just an effective action, or for us it's going to be what we call usually a Ginzburg-Landau action. And what we're going to do now is use precisely these formulas over here. To do that, we have to have an expression for the free energy. Now, the free energy in general, against Landau potential, is going to have three terms. The one in the middle is what we use when we want to study mean field second-order phase transitions, which we expand in powers of the order parameter according to Landau. But apart from that, we're going to have gradients, so spatial gradients of the order parameter that we can include, and also a source term that couples the external source with the order parameter. And if we use precisely this formula for the free energy and take functional derivatives, we can find the conserved currents of our system in equilibrium. So these formulas over here follow from precisely this prescription. And one last thing about equilibrium is that we say that we are in equilibrium when we minimize our effective potential. So we are on cell. And this is why we have to put this extremality condition on, apart from this assumption over here. So we say that the free energy is minimized as well. And this is the equation that gives us the order parameter in terms of the rest of the thermodynamic variables. So all this was about equilibrium. What happens when we include dissipation? This is what we want to do when we study hydrodynamics. So apart from the formulas we had, we're going to have new terms in the stress tensor of the current and in the equation I wrote down earlier about the time evolution of the order parameter. So all these red terms are new terms that include dissipation. In order to build them, we have to have a certain perturbative scheme. And as usual in hydrodynamics, as I said in the very beginning, we always want derivatives to be small. So we have one parameter, which I call here lambda, which just counts how many derivatives act on our variables on the variables of our theory. But contrary to usual hydrodynamics, we also have another small parameter, and this is precisely the distance from the critical point. And these two scales actually compete in our theory. So in a mean field argument, we would say that the order parameter scale is like epsilon, which quantifies somehow the distance from the critical point. And we have these two scales. And in principle, we can build our causative relations in a double expansion of our theory. But in the end, we want to solve the equations and find something useful. So we have to relate somehow these two scales. In order to do that, the simplest thing we can do is to say that actually the time evolution of the order parameter is fixed by this calligraphic f here, which is just the functional derivative of the free energy. Remember this expression over here? This is just the derivative of the free energy with respect to the order parameter, which we said that in equilibrium this is small. But what happens when we're near equilibrium? This is probably something almost zero, but not exactly zero. It is something small. So to study the dynamics, we want to relate these two terms over here, the time derivative of the order parameter and the derivative of the free energy with respect to the order parameter. And if we do that, in order to study the coupled dynamics, we see that we have to satisfy this scaling in between the two scales that I referred to before. So we're going to take lambda, which counts derivatives, as scaling like the epsilon squared, which again, I remind you, epsilon counts the distance from the critical point. So this is how we built our perturbative scheme. When we do that, and be careful about on-cycle relations and things that I may talk about a bit later, we end up with this positive relation. So we have a dissipative part for the stress tensor for the current, and this E dissipative here is what is going to give us the time evolution of the order parameter. So we have terms, as usual in hydrodynamics, we have terms with derivatives of our fluid variables. But on top of that, we have terms that include the derivative of the Kailidis potential with respect to the order parameter, which appears here, here, and in the last term over here. I want to draw your attention to this last term over here, because it turns out that previous studies, in particular this paper over here back in 1980s from Kailidis Polydoros, wrote almost this thing. Okay, they wrote this thing in a non-relativistic setting, and somehow we generalized this in a Lorentz invariant system, but they missed this final term that is important because it has, we can see it in perhaps in experimental prose, we can see it in Green's function, we can see it in quasi normal modes. So it affects physically our system, this extra term with the zeta p coefficient. As I said, we want to put phenomenological constraints on our theory. So we have on-cycle reciprocity, which imposes time reversal invariance to our system, and we have Endel production, and this just gives us these relations among the coefficients of our theory. And as I said, in order to build our theory, we took this scaling between the two scales that we have at hand. What happens when they don't scale like that? In particular, let's imagine that we take derivatives to be much smaller than the distance from the critical point. If you remember the first plot over here, if the derivatives are much smaller than the distance from the critical point, we must get back superfluid hydrodynamics. And if the derivatives are larger, so we are close to the critical point, we must get normal fluid hydrodynamics. And this is a consistency check for our theory. And if we take this theory that we build over here, and we take these two extremal limits, indeed, at the one limit at lambda much smaller than the distance from the critical point, we get superfluid hydrodynamics, and in the other regime, we get normal fluid hydrodynamics. Probably I have to skip this slide. Now, Aristos told us previously about holography. I'm going to tell you about how holography can actually tackle exactly the same system. Holography is a duality between our field theory, our system, the system we want to study, and a theory living in one dimension higher, which also includes gravity. So we have a correspondence between the stress tensor of our theory and the metric that lives in this higher dimensional space-time. The current is actually dual to the gauge field of our theory. And because we want to study a thermal system, we must include a black hole in the bulk of our space-time. And this models the thermal state of the superfluid. In particular, the duality includes this specific point over here, that when we have gauge symmetries in the bulk of this high dimensional theory, we have global symmetries at the boundary, at our field theory side. So since superfluids by definition include a global symmetry, a global U1 symmetry for us, we must have a U1 gauge symmetry in the bulk of the space-time, in the gravitational theory. And in fact, we can model a superfluid through holography by such an action, an Einstein-Maxwell action. So this is R is just a rich scalar. We have a complex scalar that is dual to our orbit parameter, and a gauge field that is dual to the current of the U1 that we want to study. And the same story holds. So above a certain temperature, we have the normal phase of our system. Below a certain temperature, we have the broken phase of our system, where the order parameter becomes non-trivial. And we can build such solutions by just solving again the Einstein-Maxwell charge scalar equations in the bulk of the space-time and model these thermal states. And we can go one step further and study the linear dynamics around such states. And we can again use a certain perturbative expansion, the way we did when we built our effective theory, and somehow relate the derivatives with a distance from the critical point, exactly as we did before. And again, the first thing we're going to get is thermodynamics, no derivatives, no anything. But at subleading order, we're going to have a dissipation. And in fact, one would have to actually solve the equations of motion, the ODEs that one gets, in order to extract this subleading part over here. This is not trivial at all. But it turns out that there is a systematic analytic method in order to obtain this subleading part. And you don't have to solve any equations at all. And if one does that and apply this symplectic current technique, one can get this subleading part of the linear perturbations in the bulk of our spacetime, extract the dual stress tensor and current, and compare with what we found before in our EFT. And it turns out that we get exactly the same thing. So in holography, so for holographic superfluids, at least, we know that our theory is correct. In particular, we can reproduce the same constitutive relations with the same zeta p, which is non-trivial for our superfluids. And another thing is that our theory gives us the transport coefficients of our theory in terms of the fields in the bulk. So this phi over here is the value of the scalar field at the black hole horizon. One last thing I want to mention is that apart from tackling the problem analytically, one can do numerics and solve the bulk ODEs. And this is what usually people do in applied holography. We can solve the bulk ODEs numerically and obtain the low-lying quasi-normal modes of our system from the poles of the Green's function of our dual field theory. Here, what I have plotted is the usual sound mode of usual first sound of a superfluid for with respect to the wave vectors. And in particular, I have plotted the first derivative of the real part of the dispersion relation. This is going to give us what we would call the sound velocity. The green line over here is the analytic result that we get from our method, and the dashed line are the numerical solution. As you can see, we can reproduce the dispersion relation in a very good manner across a wide range of wave vectors. And what is more interesting is that we can get the two plateaus, one on the right side and one on the left-hand side over here. What we are seeing is basically the previous thing I said before, that when we go close to the critical point, we must see somehow traits of the normal phase. But when we go away from the critical point, we have to find superfluid hydrodynamics. And this is precisely what happens. At large wave vectors, we are seeing the fluid velocity, the speed of sound of the normal phase. But when we go at a much smaller wave vectors, so far in comparison far away from the critical point, we're seeing the speed of sound of the broken phase. And these are precisely these two plateaus. But our critical theory can also model the exact interpolation between these two in the manner you see. And in fact, one can do the same thing for other modes of our theory. So for the second sound mode that characterizes superfluids. And again, we see a similar behavior. And one last thing is this one. So in order to see whether this extra new coefficient that we found is important, what we did is that we plotted the analytic result for the gap of the amplitude mode, this extra degree of freedom that you get precisely because you are close to the critical point, including this coefficient. This is the blue line on top. And we took the ratio with a numerical result. We can do the same thing without including this new coefficient. And this is the red line over here. You can see that both lines, when we go close to the critical point, so when T over Tc is almost equal to 1, both converge. Okay, this is what we expected. But the thing is that our theory is better than that, because as you see, for a wider range of temperatures, we can model the gap of the amplitude mode, even at temperatures that are almost 0.95 of the critical temperature. And this explains why this extra new coefficient is indeed important phenomenologically. So in summary, we built a theory for nearly critical relativistic superfluids. And we found an extra coefficient compared to previous works. We have studied holographic superfluids analytically and numerically. And what I haven't discussed is that in one of our papers, we also built the corresponding Kailidis effective theory for our system. In comparison to hydrodynamics, you don't build your currents with respect to your variables. You have a certain effective action. You expand it again in a derivative scheme in terms of your effective variables. And just by having this effective action, you can derive the causative relations of your theory and everything. And this is what we did. And we arrived, at least at the classical level, we arrived exactly at the same effective field theory. And somehow, what we can do is study fluctuations, because remember, hydrodynamics is a classical theory, but one can study thermal fluctuations for his system. And in particular, we all know that thermal fluctuations are very important, especially when you go close to a critical point. And this is something that we'll have to look at further. And another application, another step forward, would be to apply the same analytic techniques in holography and extract EFTs for other systems that spontaneously break translations. For example, what happens when translations are broken, and perhaps study their hydrodynamics and why not their nearly critical dynamics for such systems which break translations. So, yeah, thank you.
Question? Yes.
So you suggested that you can take epsilon, which was T minus Tc to 0 or small compared to derivatives in your theory and recover ordinary hydro. Would that suggest that ordinary hydrodynamics should apply all the way to the critical point? Because that's not what I expect, right?
In principle, the critical theory that we are talking about, yeah, in principle, it could be applied even at the critical point. But okay, all this is we're hiding under the carpet the large thermal fluctuations. If we're talking about mean field, right, in principle, our theories can model arterially close to the critical point.
Hey, your theory, yes, but what you're, I mean, okay, but you were talking about how you can recover ordinary hydrodynamics in the limit when epsilon was much smaller than lambda.
Oh yeah, okay,
right,
yeah. So
I don't understand why that should be true, because in the limit epsilon goes to 0, you are approaching the critical point.
Yeah.
And then I don't expect classical hydrodynamics to apply at all.
What happens is the following. Here, the thermal state that I'm talking about is very close to Tc. So this plateau on the right-hand side appears exactly because of this reason, that we are modeling a system that is close to the critical point. If we try to study the same interpolating behavior far away from the critical point, we wouldn't see this right-hand side plateau. We wouldn't see any trace of the thermal phase. Exactly because we are close to the phase transition, somehow the branches over here know that, because you know the normal phase branch continues even in the broken phase, even if it is unstable. Somehow these two have to interrelate, and this is what we are seeing.
And second question, like, of course, near the critical point, the bulk viscosity has to blow up, right? So, which is another way of knowing that classical hydro should break down, because it only works assuming that the transport coefficients are regular. So, like, can you recover from your theory the blowing up of the bulk viscosity near the critical point?
Yeah, but for this particular thing, you don't need the critical theory.
Right.
So, if you apply the symplectic current method I talked to you about before, so you consider a holographic system, you try to extract the effective field theory of superfluids, not nearly critical superfluids, superfluids, and extract the hydrodynamics of superfluids. We are going to get specific expressions for the bulk viscosities of the superfluid. And all this scale as 1 over the order parameter square. So even
from the effective theory, you can probably integrate out the amplitude mode.
Yeah.
And then when you go close to the critical,
even outside, that's right. Even outside holography, you can take our effective theory, our nil critical effective theory, and say, okay, I want to study lambda's derivatives much smaller than the distance from the critical point. what I mean by that is I take the parameter and I solve in terms of the other hydrodynamic variables. So I integrate it out.
That I understand. Then you're far away from the critical
Yeah.
point.
And when I do that,
Mhm.
I can get expressions, specific expressions for the bulk viscosities of the superfluid
Mhm.
phase. And these expressions, again, scale in the same way. They have the value of the order parameter as 1 over the value of the order parameter squared. So our effective theory knows this as well, that if we want to study, if we insist to study superfluid hydrodynamics close to the critical point, we're going to have divergences.
Okay, well, in the interest of time, let's thank Polydoros again.